as indicated earlier, the moment of a force or torque is given by R cross F, where R is a vector from the origin to any point on the line of action of the force. If there are many forces, then the total torque is going to be equal to sum of all these torques, which is going to be summation R I O cross F I. Let us see that through an example. So, if I am calculating the moment tau, which is R, I am dropping O now, it is understood that it is depending on the origin, cross F is going to be equal to its component x direction is going to be equal to y f z minus z f y plus component in the y direction is going to be z f x minus x f z plus the component in the z direction is going to be x f y minus y f x. So, let us take a simple two dimensional example. Let there be a force of 20 newtons acting along the line which is passing through say 1, 2 and 3, 3. So, that if I were to write the force as a vector, it would be 20 times a unit vector in this direction, which I can write as 20 times a vector in this direction would be 2 I plus j divided by square root of or the magnitude of this vector 2 I plus j, which will be square root of 5. So, this is the force that is being applied. So, the force that we are applying is F equals 20 2 I plus j over square root of 5. It is being applied along the line which is passing through 1, 2 and 3, 3. Let us calculate the torque about the origin by first taking R from 0 to 1, 2. So, that this vector is going to be I plus 2 j and we are crossing it with F, which is going to be nothing but I j k, the determinant way. I is 1, 2, 0. For the force, it is 40 over root 5, j component is 20 over root 5 and 0. This gives I component 0, j component 0 and k component is going to be 80 over root 5 minus 20 over root 5, which is 60 over root 5 k. That is the torque. What will torque be if I take R instead to be the vector from 0, the origin, to 3, 3? Let us calculate that. So, that vector is going to be 3 I plus 3 j. Force of course is 20 over root 5, 2 I plus j newtons. So, if I calculate torque, which is R cross F, it is going to be equal to I j k, this determinant, 3 3 0, 40 over root 5, 20 over root 5 and 0. Again it gives only non-zero component in direction k, is going to be equal to 60 over root 5 minus 120 over root 5, which is minus 60 over root 5. Okay. The direction seems to be opposite. I must have made a mistake in the previous part. Let us check that. And yes, indeed there is a mistake. This should be minus, this should be plus. So, in the previous part also the answer was minus 60 over root 5 k, and this part also the answer we get is minus 60 over root 5 k. And therefore, you see that no matter where I take the vector r to be along the line of application of the force, the torque comes out to be the same. This is also an example of transmissibility. Of force vector that we talked about in the previous lecture. As I said earlier, if there are many forces on a body, origin x, y, z, there are many forces working F1, F2, F3, F4 and so on, then the total torque would be equal to summation of individual torques, which will be equal to R1 cross F1 plus R2 cross F2 plus R3 cross F3 and so on, which is equal to summation Ri cross Fi, where Ri is the vector from the origin to any point on the line of action of the force Fi. If the forces are concurrent, that means they all meet at some point, this may be one force, this may be the other force, this may be the third force, fourth force, fifth force and so on, then the torque, I can take this point where they meet to be the point where I am going to take the torque displacement, and therefore, this is going to be Rj. Let us call this Rj cross Fi, which is equal to Rj can be taken out because it is the same for all forces, cross Fi, which is nothing but Rj cross F total. So, if all the forces meet at a certain point, the torque due to all the forces is equal to the torque of the total force cross with the direction up to that point. This is known as Varignon's theorem, and true only when all the forces are meeting at a certain point. In general, since the torque is origin dependent, therefore, if I take two particular frames O and O prime, x, y, z, x prime, y prime, z prime, tau O is not going to be equal to tau O prime for a given set of forces F1, F2, F3, F4 may not even cross them, F5 and so on. However, there is a very special circumstance under which the two torques are equal, and that is when summation of Fi is equal to 0, and I am going to show that to you. Let us take two different frames O, O prime, x, y, z, x prime, y prime, z prime. Let the distance vector from displacement vector from O to O prime be r. I am going to draw in green the forces. Let this be F1, let this be F2, let this be F3, let this be F4 and so on. Then the torque about O prime is going to be equal to R I prime cross F I summed over I, and torque about O is going to be summation R I cross F I, where R I and R I prime I take to be the vectors. Let me draw them in blue, touching at the same point. So, let us say if I extend this force like this, this could be R1, this could be R2, and up to this point this is R1. Or for F4, this is R4 and this is R4 prime. Oh, this is sorry, this should be R1 prime. So, if I now take the difference between tau O prime minus tau O, this is going to be equal to summation R I prime minus R I cross F I. And from the figure it is clear that this is R4 prime, this is R and this is R. So, R I prime plus R is equal to R I, like R4, this is R4 is equal to R plus R4 prime. Similarly, R1 is equal to R plus R1 prime. So, R I prime in plus R is in general R I, and therefore, R I prime minus R I is equal to R with a negative sign, and therefore, tau O prime minus tau O is equal to summation I minus R cross F I. R being the same vector, I can write this as minus R cross summation I F I. That is the difference between the torques taken about point O prime and point O. So, let us write this again, tau O prime minus tau O is equal to minus R crossed summation I F I. R is a vector from O to O prime. Thus, if the total force summation F I is equal to 0, this implies tau O prime is going to be equal to tau O. The torque becomes independent of the origin because I took O and O prime arbitrarily. This is what I promised you earlier. I will show that if the total force on a system is 0, then the torque is independent of the origin. No matter about which point I take the torque, it will always come out to be the same. A very special case of this is something called a couple, which is used in engineering mechanics quite a lot. And what is a couple? A couple is, suppose I take a body, apply a force in one direction, apply a force in the opposite direction minus F, and they are displaced parallelly from each other by a distance d, then net force F minus F is equal to 0, and the torque need not be 0 because the forces are displaced from each other is going to be magnitude of F times d, where d is the perpendicular distance between the two, and this is known as a couple or couple moment. It is indicated either by this symbol, where these two arrows show the forces applied, or a symbol like this. So, it is a pure moment without any force. Thus, a couple is a force or two forces F minus F displaced by parallel distance between them d, and its moment is given by F d. Since the net force is 0, the same couple can be generated by different kinds of forces. For example, I could have a force F 1 going the other way minus F 1 displaced by distance d 1 from each other. This would be equivalent to a force F 2 which let us say is minus F 1 divided by 2, but the distance d 2 which is twice d 1, which will also be equivalent to a force F 3 minus F 3, let us say, which is equal to 3 times F 1, but displaced from each other by a distance of d 1 over 3. They all three of them represent the same couple, because the net force is 0. So, there is no effect of the force. So, let me just recap what all did we do in this lecture. 1, we looked at vector products in detail. Then we looked at equilibrium conditions and found that summation F I is equal to 0 and summation torque I is equal to 0 are both necessary and sufficient condition to ensure equilibrium. Then we started looking at different aspects of equilibrium separately, and third, we looked at moment of a force and found that tau I, the total torque tau I summed over is equal to R I cross F I is origin dependent, but becomes independent of origin if total force is 0. Let me rewrite this again. Tau is independent of origin if summation F I is equal to 0, and then we looked at a very particular special kind of torque under these circumstances called a couple, which is two forces, equal and opposite forces separated by a parallel distance d. In this case, the force magnitude times d is the couple moment, and the direction you can find by right hand rule or the cross product rule yourself. In the next lecture, we will look at how to define the moment about an axis or a couple about an axis, and then go on to discuss other things about equilibrium.